benefit here is in the reverse bias now, I can go up to 950 or 920 volt compared to when I was having Schottky diode, which is only up to 250 if I don't have any edge termination versus 4 to 500 voltage if I have a edge termination. So in terms of breakdown, I'm gaining a lot compared to the Schottky diode, and also the on resistance is only slightly decreasing. So that is the reason that we can use junction bias Schottky diode in power applications, so that we can have a low on resistance versus, and also we can have a high blocking voltage so that we can easily use them in application where we want to, let's say, block almost 900 or 800 volt in terms of background voltage. So when I was saying, so this is the simulation that we can also do. So all these results are experimental, but when I can go back and I can simulate the devices and see what are my electric field, for the Schottky diode, when I don't have any edge termination, so here is the metal that I was showing, and you can see at the edge of the metal you have electric field crowding, meaning your electric field at the edge from this graph you can see here. In the center, it's almost 1 megavolt per centimeter, but when you go at the edges of the metal contact, which is here, the electric field spiked up, and that is the reason why you see the breakdown around 300 voltage, because the electric field is very high near the contacts, and that breaks down your device. So when you have a junction bias Schottky diode, because of this P region that we implanted and then we activated, so that now push the electric field inside the bulk, and that reduces the field at the contact. And also when you have where you have a Schottky region, you also see less electric field, because here you can see this is 3 megavolt per centimeter versus here you have almost 1.5 megavolt per centimeter. You can see from this cross section, from this graph in the bottom. So from this cut line where you have P and N, the electric field goes maximum around 3.3, but that is still in the bulk, not at the metal surface. And when you cut a line at the Schottky region, you can see the electric field around 915 volt is less than 2 megavolts. So that is the reason you can go up to 915 volt versus in the Schottky diode, because the electric field, even at the lower bias, went very high because of the electric field crowding. So that's the advantage of junction bias Schottky diode that we can use in power device application, so that we can get low on resistance as well as we can get high breakdown voltage. And one thing I forgot to mention is that the breakdown voltage of the junction bias Schottky diode is same as the PN diode. The only difference between the Schottky diode and PN diode, the PN diode turns on in gallium nitride around 3 or 4 volt, whereas Schottky diode, as I was showing here, turns on at 0.5 or 0.6 volt, which is low in compared to the PN diode, and lower voltage also gives you lower losses. So you definitely want to use Schottky diode, but you also want to use junction bias Schottky diode so that you can get the similar breakdown as PN diode. So junction bias Schottky diode is best between both worlds. In terms of breakdown, it's similar to PN diode. In terms of on resistance or turn on voltage, it's similar to the Schottky. So that is why we were behind this project, that we wanted to make the junction bias Schottky diode using P-type implantation in gallium nitride, so that we can compete or we can provide even better device performances than silicon and silicon carbide. And that I can show here using this matrix, that all these different dots or triangles or squares that are from silicon carbide, the current technology. And you can see the current at 1000 volt or around 950 or 1000 volt right now. The junction bias Schottky diode using silicon carbide has on resistance around 10 to 20 milliohm centimeter square. But when we made this gallium nitride JBS diode, the on resistance was only 0.6 milliohm. So that is almost a 1 to 1.5 order higher or lower on resistance for the same breakdown voltage application. So meaning I can pass more power or having a lower losses compared to if I use silicon or silicon carbide versus my gallium nitride devices. So that is the reason why we wanted to make this p-type implantation uh, possible in gallium nitride so that we can make better devices than other technologies. And just to prove this concept, we also wanted to make a higher breakdown voltage. For example, this 1000, if I can go to 2000, 3000, or even 5000, if I can still use my the selective area p-type implantation technique and get the device scale to 2000 volt or 3000 volt, then I can surely say that this magnesium implantation technique that we developed is reliable and we can make any devices out of it, right? So for 2 kilovolt application, the only difference we did is that the drift region thickness or this n-type region thickness, because if you want to block more voltage, you need more material. And then you can now design the thickness and doping of the material based on the required breakdown voltage. There are already theoretical equations that we can use. And we can also simulate, as I was showing in one of the simulation results. So for the 2 kilovolt application, we now need thicker drift region or thicker material, but the top p-type region, as I was showing you, the islands, those are the same. We can still go with the same implantation dose and energy, and we can activate them at the same temperature, time, and also the device fabrication. Once you activate them, you put the different metal contacts because you need to probe them or you need to pass the current through the metals to the semiconductor. So we use the same fabrication processes. And here is the IV characteristic comparison between the Schottky diode and JBS diode. And the left graph shows in the semi-log scale. And again, the once you apply positive bias, you can turn on the device. If you apply negative bias, you turn off the device, or whatever the current you have is the leakage current, which is almost 10⁻⁹ amp per centimeter square, which is very, very low. So you can say that you have a no current when the device is off, and you have a almost 1 kiloamp per centimeter square current when the device is on after 1 or 2 volt. So the on-off ratio at ±3 is 10⁻²², and from the linear graph here, you can see the device turns on after 0.75 volt, and the on resistance for the Schottky is 1.1 milliohm centimeter square, and for JBS is around 1.9 milliohm centimeter square. And also, we try to measure the PN diode, the on characteristics. So you can see in the log scale, the device, when you apply from 0 to positive, the current starts going up. And once the device is up, after let's say 6 to 7 volt, you can see the light, because this is a direct band gap material. It's kind of an LED, right, that we have in the blue LED in the market, or white light. Those are made from GaN. Here you can see the little bit yellow light because of the defect luminescence. But the thing is that even if you implant magnesium, once you activate them, you can pass the holes. And when the hole and electrons recombine, they emit light, and you can see the light from here. So that shows that that the implantation and activation that we did, it really worked, and you can see the light from the diode. So, in terms of breakdown voltage, because we wanted to target 2 kilovolt, you can see for the PN diode, we got almost 2 kilovolt at after like 1.8 or 1.9 kilovolt, the leakage start increased and it almost breaks down at 2 kilovolt. For JBS, it's very low leakage compared to the Schottky diodes, because Schottky diode again breaks down at 300. If you have H termination, it goes to up to 1.1 kilovolt. With the JBS, we get around 1950 or around 1900. So that shows that with the same technology that we tried for 1 kilovolt, we can also scale to 2 kilovolt devices. So in terms of the performance comparison, we can see that the 1 kilovolt is here, and then we can scale it to 2 kilovolt because now once you go higher in breakdown voltage, As I said, you need to increase the thickness of the drift region or the material, and because of the larger thickness, you will also have a larger resistance, right? So the resistance also went up, but this is still better than the silicon carbide or silicon. So that's the advantage of gallium nitride compared to other materials here. Based on all this result, now I want to provide a summary. The main thing we are targeting is to get the good p-type conductivity using magnesium ion implantation, which was not developed in the literature before. And we use the ultra high pressure annealing system, which because of that, now we can go up to very high temperatures to activate those implanted species. And we can maintain the pristine surface without having any cap layer. And because of that, now we can see that all the Schottky diode and JBS diode are having a very good quality on-off ratio current. When device is on, you can get very high current. When device is off, you can get very negligible leakage. So using this developed the magnesium implantation technology, we created state-of-the-art kilovolt class GaN junction bare Schottky diodes, and we demonstrated 915 volt and also 1.9 kilovolt breakdown voltage devices. So now that technology is developed, now we can make very different complex device structures that even can replace the silicon or silicon carbide devices. So we can get more efficient power conversion. We can have very low losses, and once we have low losses, um, we can transform many different spaces where, like, power generation to storage and in power usage. So all these spaces we can use a better material and better devices. So with that, I want to thank you for your attention, and I'm open for any questions.
Thank you, Dr. Kacharia. Now the session is open for questions. I would like to request all the participants, if you have any queries regarding the research or recent in trends topics, you could please ask him. There are no further questions. I would like to proceed to thank Dr. Kacharia for such informative session, which has given us good insights over this new topic rather. So from the organizing committee, I would like to appreciate your efforts by just giving you virtual memento, wherein the actual physical memento has already been couriered to you. Thank you so much for your cooperation and time, sir.
Thank you, no problem.
Uh, all the participants are requested to join the next session at 12:30. Participants are requested to fill the feedback. Link has been already posted in the group.